Empirical formula calculations. Empirical formulae is essentially the simplest formulae of a compound. If in maths you were to report a fraction like this, 6/8, your teacher would probably say to you, simplify it. And you'd say, yeah, okay, I can simplify that because it's not in its simplest form, so 3/4 is it simplified. And that's what empirical formula is in chemistry. So a formula like this, C2H4, that could be the molecular formula of ethene, is not its empirical formula. It's not ethene's empirical formula. What we're looking at in empirical formula is the ratio between one element to another. So the empirical formula of C2H4 would be CH2. Notice that's not the molecular formula. The empirical formula is just the relationship or the ratio between one element to the other element. Now, if we do experiments, we can work out the empirical formulae of substances by measuring how much of one element reacts with how much of another element. And here is an example question. So we've got 46.4 grams in this question of iron oxide. That's of the iron and oxygen combined. That contains 33.6 grams of iron. So the first thing we need to do with that is we need to work out how much oxygen there is in that formula. It doesn't tell us how much oxygen there is. It tells us the amount of iron oxide and the amount of iron. Now, if we subtract the amount of iron, we get the amount of oxygen. And it's very simple. If I put my finger over iron, it just leaves the word oxide. So all I've done is subtracted the iron. I've taken the iron away and I'm left with the oxygen. So we just need to do that mathematically. So we've got 46.4 grams of the compound. And we're going to subtract the iron, and that will leave us the amount of oxygen left. So 46.4 minus 33.6 equals 12.8. So that compound now contains 12.8 grams of oxygen. That's what we've just worked out. Right, so now we know how much iron there is and how much oxygen there is, we can start to work out the empirical formulae. What I suggest you do is to take the space you've got available to you here and just draw a line down the middle of it, about halfway down the page. And on one side write iron, because we need to work out how much iron there is. And on the other side write oxygen, because we need to work out how much oxygen there is. Now, we need to learn a formula, the moles formula. And that is, for this, moles equals mass over relative atomic mass. I'm just going to abbreviate relative atomic mass to a capital A and a subscript R. And we're going to write that on both sides, and I suggest you do this. The more you write this down, the more you tell the examiner that you know what you're doing, and the more you write this down, the less likely you are to forget it or make mistakes. The exams are a stressful situation, so just get into the habit of drilling yourself like this each time. So moles equals mass over AR, moles equals mass over AR. We've done that for iron, we've done that for oxygen. Now we just need to plug the numbers in. We've told in the question, we underlined it, 33.6 grams of iron. That's the mass of iron, 33.6. The relative atomic mass in the question, there, Fe 56, divided by 56. Let's plug that into a calculator straight away. 33.6 divided by 56 equals 0.6. You can tell this is an exam question because the numbers are whole numbers. They often are in exam questions. They may not be, but don't worry if they're not. But they often are. So that tells us there's 0.6 of a mole of iron in that example. Right, let's do the same for oxygen. We've already worked out there's 12.8 grams of oxygen with our initial calculation. So we're going to write that 12.8 in there. The atomic mass of oxygen is 16. So we're going to divide that by 16. And we'll put that into the calculator, 12.8 divided by 16 equals 0.8. So what we can now write down here is we've done the iron side and oxygen side. Let's write it down here now. We now know the starting point of our empirical formula. Fe 0.6, O 0.8. That's what that tells us. The 0.6 has come from there, the 0.8 has come from there. This tells us a relationship between iron and oxygen in that formula. Now, to report empirical formulae, we need to report to the simplest, smallest whole number. So we can't report it like that because these are decimals. Now, there's a couple of ways you can do this. You can look at it and just, with your feel for number, understand the relationship between these two. Or you might want to do it in a slightly more mathematical way. To do it in a slightly more mathematical way, it's probably best to divide the big number by the small number. And that will tell you the relationship between those two. So 0.8 divided by 0.6. Let's do that. Equals 1.33. Okay, so that tells us this was a smaller number. So what we've done is we've made that smaller number equal to 1. So that tells us it's FE 1. I'm not going to write a 1 because remember, chemists are lazy, we never bother writing 1s. O 1.33. So there's, for every iron atom in this formula, there is 1.33 oxygen atoms. Okay. This is a bit closer to the empirical formula. It's still not there because this is not a whole number. We need to make this a whole number, so obviously we're going to have to increase the numbers on both sides because this is a ratio. If we increase this side, we have to increase this side. We're looking at the relationship between these two numbers. Hopefully you can see that that's a third, 1 and a third. So if we multiply this side by 3, that will get that third out. Okay. If we multiply it by any smaller number, it won't return us a whole number. So if we're going to multiply this side by 3, we have to multiply this side by 3. So that's going to be Fe3. It was 1, we've now multiplied by 3, it's now 3. If we multiply that by 3, it becomes 4, FeO4. And that is the empirical formula in this of iron oxide in this question. And that's the answer we need. As I said, you don't need to go through this last step if you've got a feel for number. Look at these numbers again, Fe 0.6, O 0.8. The fact it's a 0 in there is not important. We're looking at the relationship between these numbers. So in exactly the same way as we started this explanation, 6/8 is 3/4. When simplified, you could just go straight from there to there. And that's possibly how a lot of students will do it come exam time. Looking at exam questions, I have an exam question here on empirical formula. This is the June 2014 EdXL chemistry high level paper for GCSE, and we've got a question here about iron and chlorine to check we can see all that. Yes, we can. So when we get questions like this in the exam, remember always underline everything you've got. This is an easier question than the example we looked at a moment ago. It tells us a compound of iron and chlorine was formed by reacting 2.8 grams of iron with 3.5 grams of chlorine. So in this occasion, it doesn't give us the mass of the compound and make us subtract. It's given us the mass straight away of the two elements that make up that compound. It's given 2.8 grams of iron and 3.55 grams of chlorine. So exactly the same way we did a moment ago, a line halfway down the page. That's right here, the moles formula. We must learn this. Mass divided by atomic mass, relative atomic mass. I've used the abbreviation AR. Do the same over here. Moles equals mass divided by atomic mass. This side will do the iron, I think. So let's label that iron. This side will do the chlorine, so let's label that chlorine there. And now we need to plug the numbers in. 2.8 grams of iron. 2.8, the atomic mass of iron, 56, there they are, divided by 56. Let's put those numbers into this calculator. 2.8 divided by 56 equals 0.05. Let's do the chlorine now. So we've got 3.55 grams of chlorine. 3.55 grams of chlorine divided by 35.5. Those of you good at mental arithmetic probably don't need a calculator for that. I'll put it in here just to show that we can do it with the calculator or without, it really doesn't matter. 35.5 equals 0.1. Equals 0.1. Okay, so we can now take those numbers down here, so these now become our empirical formula, or heading towards it. Fe 0.05, O 0.1. So iron oxide like that. So again, if you've got a feel for number, hopefully you can see the oxygen is bigger 0.1 than the iron, so there must be more oxygens in the compound than there are ions. If these numbers were the same, it would be the same. It would be a 1-to-1 ratio. They're not. This is bigger. We can see that's bigger, so this number must be bigger in the formula. The question is, how much bigger? If you've got that feel for number, you can see possibly that is twice as big as that. So that would suggest the formula is going to be FeO2. If you don't have that feel for number, take the big number, divide it by the little number, and just do the maths. And I think if when we do that, we're going to see that equals 2, which immediately tells us we were right when we suggested the oxygen. There was twice as much of it, FeO2. And there is our empirical formula. Now for the GCSE this time, there's a twist. That's an old-fashioned exam paper, the A-star to G exam paper. We're on 9-to-1 chemistry nowadays. So there is a twist now. They may ask you to work out the empirical formulae and then give you a molecular mass, a formula mass, if you like, and ask you to work out the formula of the compound, the actual molecular formula. Right, so we've got an example of this type of question here. A hydrocarbon contains 3 grams of carbon, 0.5 of a gram of hydrogen. The relative formula mass of the molecule is 56, and it wants you to calculate the molecular formula. So the first thing we need to do is calculate the empirical formula. Same as before, line halfway down. Carbon and hydrogen are the elements, so carbon, hydrogen, moles equals mass over atomic mass. Notice every time I write these out. Okay, if we do this, you learn it, you won't make mistakes, you show the examiner you know exactly what you're doing. Even if you do make a mistake, you'll still get loads of marks. So just get in the habit of writing this stuff out. 3 grams of carbon. 3 grams, atomic mass of carbon 12, 3 divided by 12. Okay, could put that on a calculator, but hopefully you all know it's 0.25. If you don't believe me, put it in. This time now, half a gram of hydrogen, so 0.5 divided by the atomic mass of hydrogen, 1. So 0.5 divided by 1 equals 0.5. Hopefully you didn't really calculate for that one either. Okay, and we've now got our empirical formulae. It's going to be C, 0.25, H, 0.5. Again, that's not the empirical formula quite, because we need to put this into the smallest, simplest whole number. This number here is smaller, the carbon is smaller, so there must be less carbon. The hydrogen is bigger, so there must be more hydrogen. The question is how much bigger? Well, 0.5 divided by 0.25, that's going to equal 2. So again, just like the example in the exam paper a moment ago, there's twice as much of one than there is of the other. There's twice as much hydrogen than there is of carbon, so the formula is going to be CH2. That's the empirical formula. Again, if you don't believe me, just take the 0.5 and divide it by 0.25. Okay, and that's going to equal 2. That tells you that's the one. The smallest number is the 1, C1. The bigger number we've divided by the smallest number. That tells us there's twice as much of it, so it's CH2. So that's the empirical formula, not the molecular formula. Now we know the molecular mass, 56. What we need to do is we need to work out the formula mass of CH2. Okay, and then we can divide the two of them. Carbon has got an atomic mass of 12. Hydrogen has got an atomic mass of 1. Okay, but there's two of them. Plus 1 equals 14. So if we take that formula mass now, 56, and divide it by 14, that 14 there, 56 divided by 14, it tells us there's 4 of them. So this hydrocarbon here must have 4 units of CH2 in it. So the molecular formula has to be C, 4, 1 times 4, H, 2 times 4, 8. And there is our answer.